Please welcome Simon White.
Thank you very much. So the very good thing about virtual universes is that you can see the dark matter. So I'm going to talk today about what we've learned, or we think we have learned, about the dark matter from numerical simulations. And so, let's see if this works. I think I was very lucky in this because I came into the field in the early 1970s, and this is a time both when computers actually started to be able to do something about simulations, and also at a time where the dark matter problem started to come into focus. So when I started, this was the biggest telescope in astronomy, a 5-meter telescope at Mount Palomar, built more or less like a battleship. That was the main astronomical instrument. This was the main computer in Cambridge. It's called an IBM 370. It was huge. I was in an astronomy department. We didn't have this. This was hidden away in a building in the center of town. In fact, I never actually saw it. What I did when I was a student was sit at these things. Now, you might think these are terminals, but no. These are little keyboards where you punch cards. And each computer instruction for the computer is put on a punch card, and you do this. They had a certain number of columns. You had to get it just right. And then when you had all the cards together, they were in a big box, like, is this going to work? Like this one, full of cards. And then this is how you put the instructions into the computer. But our department didn't even have a card reader. So to put the instructions into the computer, I had to put these big box of cards into the basket of my bicycle, cycle in the rain across the street to the neighboring physics department, where there was a machine like this. We could actually read the things in. So this was how computing was done at this stage. So maybe in Los Alamos, when Jim started, it was better, but I think he said he was using punch cards, so it was basically the same. So this was how we started. So why did I get into dark matter? Well, I think for me, personally, it was these two papers. This one received April the 10th, 1974. This one received May the 28th. So actually, I think this one, the Estonians do belong on top, judged by the date. These two papers you've heard about earlier basically made the same point, and this was evidence, mostly collecting evidence from various sources for very large distributions of material around galaxies. So for example, here you can see the first line of the abstract here. The mass of spiral galaxies increases almost linearly with radius nearly 1 megaparsec. 1 megaparsec is a big distance. That's beyond the Andromeda Nebula. So far, far beyond where there were rotation curves. And these are the plots of the data. So this one you saw earlier. This is the one from the Peebles, Oestreicher, and Yahil. And you can see this is logarithm. So this is 1 megaparsec. So the Andromeda Nebula is out here somewhere. That's where this T is for the timing argument. And this is the amount of mass, and the mass is going up. So when you get way out here, it's much, much more than the mass of all the stars. And this is the same point from the paper by the Estonians. You see, by the time they get out here, hundreds of kiloparsecs, they're up to 10 to the 12, 10 to the 13 actually here. Solar masses is the number they put here, which is about 100 times the mass in the stars. So this impressed me. The rotation curves, we heard a lot about it. I never felt very impressed personally because it was always going out another factor of 2. And as we heard, factors of 2 in astronomy, you can easily push one way or another. This was going out factors of 10 and factors of 10 in mass. And that really seemed to me at the time very impressive. So that's why I got particularly interested in the dark matter. This was just as I was starting as a graduate student, so it seemed really exciting at the time. The first simulation that I know of that was carried out specifically to test a particular theory of structure formation was in this paper. This is a famous paper about a theory for the formation of nonlinear units in astronomy, in galaxy formation, by Press and Schechter. Most people have forgotten that actually in this paper they did carry out numerical simulations. You can see here the results of numerical experiments on 1,000 bodies are presented. These appear to show new nonlinear effects. So the reason for doing the simulations was to follow what happens when the universe stops being smooth and lumps collapse out when it goes nonlinear. And this was the first example of trying to test the nonlinear effects of a particular theory from this, and actually they got the wrong answer. So this is probably why one of the reasons that people didn't believe simulations for a long time afterwards. They got what they thought were new nonlinear effects, and they got growth which was faster than was expected. This turned out to be because of numerical limitations. My own first experiments, were shown here. This was trying to follow a cluster of galaxies, similar to the calculation which Jim had done at Los Alamos a few years earlier, where this was something, it was a region supposed to be a cluster of galaxies expanding with time, and you watch how it gets lumpy. So this is expanded, this bar here is the same length in all the pictures, the physical length, so that it's actually expanded. If you look at these plots, they look funny. That's because there were no plotters available at the time. You couldn't make images. So these plots were made by taking line printer paper, which everyone has probably forgotten, where there's a huge printer which prints things on sheets and sheets of paper, and then using the characters in the printer to represent the objects. And then you make it smaller, and it doesn't do too bad a job at showing the plot. So that's how this was done. And what you see is that it started smooth. It's gone up by about a factor of size, and it became very lumpy. And then the lumps fell together into two big lumps, and it fell together. So the motivation for this calculation was, in fact, a dark matter issue. At the time, no one knew what the dark matter was and how it was attached to the galaxies. So this was actually trying to test whether the dark matter could be attached to the galaxies in proportion to their brightness. And what happens if that happens is all the bright galaxies, which are then the most massive ones, end up at the middle because they sink. And in fact, that was what I wanted to test when I did this. And in fact, they all sank much more than the real ones did. And I concluded that maybe the dark matter wasn't all attached to the galaxies, but some of it was somehow in between them. But actually what this got remembered for was I was just lucky, because a few years later, when people could make X-ray images, they could make images of clusters in the X-rays, and you found some which were irregular, and some which had two lumps, and some which were centrally concentrated, which looked just like these pictures. So sometimes you just get lucky. This, I think, a point I wanted to make about how people were thinking about dark matter in this period. So these are three papers. If you look here, this is amazing. These are three very well-known papers, one by Joe Silk, one by Martin Rees and Jerry Oestreicher, and one by James Binney. This one was submitted April the 5th. Sorry, get this right. It's April the 5th, July the 7th, July the 8th. So the three famous papers saying very similar things, all submitted within a month of each other. So clearly there was something in the air. They were trying to study galaxy formation. And what they were interested in is why galaxies are the size they are. And they realized that this might be something to do with the cooling processes in the gas. But the reason I put it up here, and I think it's relevant now, it's very interesting. These had a lot of analysis and had a plausible story about the size of galaxies, but they nowhere mentioned dark matter. Okay? So, for example, if you look at this plot, which is the most famous one from the recent Oestreicher plot, this is the density of a gas cloud and its temperature, and they showed there are regions where gas clouds can cool off and collapse very quickly. That's later got called cold flows. There are regions where it can cool off slowly, and regions where it doesn't cool at all. And the boundary here is something like the mass of a galaxy. Nowhere does dark matter appear here. This is just gas. They had an idea, if they were thinking about the dark matter at all, that somehow it formed at the same time as the other components as it collapsed. But things were changing very dramatically at this time. So even a year later, and I wrote my own paper on this subject with Martin Rees, the mood had already shifted. So here you can see it's two stages. So the luminous content of galaxies comes from cooling of residual gas in the potential provided by the dark matter. So the idea had already shifted that somehow the dark matter was there, made the gravity, and then the gas came later. And this was a very switch change, but you can see also from the first part here that we still thought that this was probably small dark objects, small stars. We weren't thinking then of elementary particles. In fact, I looked through the paper, I thought after surely we must have mentioned new particles somewhere, but no, there's nowhere mentioned in this paper anything about elementary particle dark matter. And if you look at the simulations at this time, this was the last of an era. There were no agreed initial conditions from which you should start to follow things. And so what people took was extremely idealized initial conditions, like just random points in space, and saw how as the universe expanded, they clustered. So this is the last of these, and you see this is supposed to be the clustering of dark matter. And although this was just the dark matter, it was compared with the distribution of galaxies. And people didn't really understand the relation between the dark matter and the galaxies, and so they just said, well, let's assume that galaxies are randomly chosen dark matter particles and do a comparison. This was what was done. So I think, for me, the big change here came with this paper, which no one mentioned this morning, but this is what actually started, from my point of view, people really thinking about particle dark matter. It's because there was this paper by a group of Russians claiming to measure the mass of a dark matter particle. They measured a mass of the electron neutrino between 14 and 46 electron volts from the endpoint decay of tritium. And 30 electron volts, they knew, was exactly what you needed for the electron neutrino to supply all the dark matter in the universe. So here was an observation, it was an experimental claim to measure a mass of the neutrino, which would mean it had to be the dark matter. And it's very interesting. It's a short paper, as Russian papers often were. It thanks Zeldovich, who was a famous Russian cosmologist, but nowhere mentions that these neutrinos would be the dark matter. Which is, since Zeldovich was one of the persons who was most pushing for the idea that neutrinos were dark matter, it's extraordinary that you should find the right mass and not mention it. So there's some interesting historical background to that which I don't fully understand. Of course, this turned out to be wrong, but it really made everyone think seriously, because if it had been correct, that was the answer. So people made experiments, numerical experiments, with what this looked like. This was the first one. This was published in 1983, which was actually carried out around 1980, but in Russia, so it took 3 years to get out into the Western journals. So this was the first experiment that I saw, which was supposed to represent what structure would look like in a neutrino universe, and it had these big lumps linked together by filaments. So very large structures. But was a bit vague at exactly what the scale was and where the galaxies should be. So I think what really changed the game here were calculations which said if the universe is made of massive neutrinos, this is what the initial conditions should look like. And these were carried out about 1980. There's a paper by Jim Peebles, and then a paper by Bond and Saleh, which came out a bit later, but this work was basically going on in parallel at the time. And they calculated if the universe is made of initial conditions, what exactly the initial conditions should be, how it should start. And you can see here already, just from this, Jim concluded, in the conventional SARI, the coherence length is uncomfortably large. So what he saw, even when he first calculated with this, was it looked too big for him. He didn't make a very strong statement, because he was calculating what happens in the smooth universe before the nonlinear objects form. But he already saw that this looked uncomfortably big. So this is what they calculated. This is the amplitude of fluctuations in the early universe. This is how long they are. These are the short wavelengths over here and long wavelengths over here. What was used in that Klippin and Shandarin experiment looked like this. And this is what the real initial conditions should look like. So you can see it doesn't really look very similar. So once you have initial conditions, you can now run an experiment where you can say what things, the initial conditions actually match what is predicted by the early universe. And when you do that, then we concluded that the conventional picture appears to be ruled out. So the stronger statement here than Jim's is because now we can use the simulations to get from the linear initial conditions to the present day in the nonlinear universe, and it really doesn't look like the real universe, as you can see here. So this is a survey of the real universe, and these are predictions what the distribution of galaxy size would look like in a neutrino universe. And you can see they don't look very good. Objects are much too big compared to the things you see in the real universe. But at the same time, people were realizing, well, if it's not neutrinos, there are other kinds of particles, as we already heard. And Jim, again, calculated what their initial conditions should look like. And these were simulations from a cold dark matter universe, which look a lot better. And so this, from my point of view, was, well, this was the only extra particle known to exist, which could have been the dark matter, and it didn't work. In fact, none of the neutrinos would work. But at least we could invent new particles which could work. So then we all started looking at new particles. And in fact, this was our first paper on this in 1985. And you can see we now know that the real universe apparently has low density and a cosmological constant. The cosmological constant was very unpopular in 1985. We actually did run one model with a positive cosmological constant. If you look at the parameters here, they're actually pretty close to the real ones. And it actually was the best fit. The open models were equally good, but it fit better than the high-density ones. Nevertheless, we then concentrated on the high-density ones because the theorists were telling us that inflation said the universe had to have the closure density, and they didn't like a cosmological constant. So we concluded it may be possible to reconcile a flat universe with observations of the galaxy distribution by playing various tricks. And this then became the standard model for a while until we eventually gave up because it wasn't going to work. But this is an example of what things look like in these low-density universes. So this is the real universe, and these are simulated universes. You know, this is omega of 0.2. This is quite close to what we think is the present universe. It was kind of there in 1985, but we decided to ignore it because the theorists told us that this couldn't possibly be the right answer. Nowadays, things go a lot further. So this is now, you can make much better pictures with present-day graphics, and in fact, you can even make movies. So as I say, in a virtual universe, you can fly through it. And you can really go fast. You can go across the whole universe in 1.5 minutes. That's about 10 to the 15 times the speed of light. And so you see the very complex structure that's predicted from the initial conditions. So this is what the dark matter is predicted to look like. But of course, the trouble is we don't see the dark matter, as we keep hearing. You have to predict where the galaxies are going to be. So here was an attempt to do this. This simulation, this is now 2005. This was about the first simulation with a very large region where you had enough resolution you could actually predict where the individual galaxies should form. And so you can make plots like this one, where this is the real universe, the distribution of galaxies. And this is a simulated universe where you view the galaxies, not the dark matter, because you've tried to follow their formation in the same way. And then you can make quantitative comparisons. So that, I've gone in front of myself. So I think the next stage, from the point of view of the simulations, was understanding in more detail what the dark matter distribution should look like. And particular simulations are good for telling you what the nonlinear distribution of dark matter should look like. So it was about in the mid-90s that it was realized that in fact if you plot the density of an object as a function of distance from its center, you could take things, these are now all predictions from simulations, right? We don't know yet whether this is the real world, but they all look rather similar. They're dense in the center and the density falls off, and it falls off in more or less the same way. You know, small galaxy, a normal galaxy, or a cluster of galaxies, it's just the bigger things are bigger, but they all look similar. And I think the thing which was really the insight in this work is not what people usually focus on, which is what is happening at the very center of the object, but really that there's a relation between how dense an object is and how massive it is. And this is something you can actually predict from the cosmology. So with this in place, this means from your initial conditions, you actually don't need to do the simulations. You can predict more or less what objects of different masses should look like, what their density profile should be. And then we were lucky. It turned out went to a much bigger object, then you find you get something which is more or less the same law, but now of a much wider range of scales. So this is a factor of 1,000 in radius. And you can see the objects have quite complicated structure. So if we look at this is another movie to show you in these simulations what the dark matter associated with our Milky Way is predicted to look like. This is very early. This is only 100 million years after the Big Bang. You can see there are already small lumps. But everything you see in this picture is going to collapse to be the dark matter just in the Milky Way. So the rotation is just is not real. It's to allow you to see the three-dimensional structure. So imagine you're flying around and around this thing as it's forming. So here, we're 250 million years after the Big Bang. You see the many, many small lumps of material, and it looks a bit like the present-day large-scale structure of the universe. But all these lumps are all going to fall together. And as we come forwards, you can see bigger and bigger things falling. So you can see the way the dark matter is predicted to build up, according to these ideas, is through this gradual growth. And now you can see there's a single object here at the center, and this is going to just get bigger and bigger with time as all these things finally merge. And this is how structure of an object like the dark matter around the Milky Way is supposed to assemble, according to the simulations. Okay. So you can ask, what do we No. Well, the first thing you can do is this any reality to this? So this is something where observations have caught up. So now, in a sense, you can test this. So this is the distribution of dark matter around clusters of galaxies measured directly from the gravitational lensing of background galaxies. And this is a prediction. So you can see the general shape is quite good. And there are many other lensing observations. So this is an example where we didn't really know what the dark matter distribution should look like in a cluster of galaxies. You can use the simulation to say if the initial conditions are right and we understand the dynamics, this is what happens, and then you can test it. But what you notice, perhaps most dramatically when you look at things like this, is all the small pieces in here. And these are the remnants of all the different things that fell together. And in about 1999, when simulations inside computers first got big enough that you could start to see all these small structures, these two papers pointed out this appeared to cause a problem. Because what they did was count how many small objects there are inside a big object like the Milky Way's halo as a function of the characteristic velocity. Then the count from the simulation is these open circles, or on this side it's these dashed lines, and they just counted how many objects you can actually find. And this is what they found. You can see they don't agree very well with each other. There are reasons, but the basic answer is there are many, many things you predict to see in the dark matter and not very many real galaxies there. And this appears to be a problem. And this is a problem along with the other problem which we heard about from Albert this morning, that the central regions of these objects appear too dense. So this was the problem. In this paper already they noted how this would affect interpretation of the dark matter. And one particular point which I think Joe will talk about after me is how this will affect the radiation you might see from the annihilation of these particles. And the reason this is important is because if there are very dense regions in the center of each of these lumps, the particles annihilate there very rapidly. They produce lots of radiation, which you might be able to see in gamma rays. So this is, for example, what the gamma ray sky might look like if that simulation was correct. This is the galactic center. There's a big glow from there. There's a big glow from all the objects in the simulation which you could resolve, all the little lumps you could see. And there's an even bigger glow predicted from all the ones which you couldn't resolve, which are even smaller. And you add all these together, and you get a predicted gamma ray sky where you would see the galactic center glowing because of the dark matter, and then all these other small lumps also glowing, and a background glow across the whole sky from all the really small things. So whether this is correct or not depends on whether these predictions from the simulations for the centers are in fact right. So then the question is, will you see it? For example, with the Garrett-Fermi telescope. People have been looking hard. They're not yet convinced they've seen these effects. The other way in which the nature of the dark matter affects things is that what the picture looks like depends on what you assume about the dark matter. So this is a prediction for cold dark matter. This is a prediction whether dark matter is a different kind of particle, which had less structure in the initial times, so-called warm dark matter. You can see all the very small lumps have disappeared. So this would be if it was an axion, you predict something like this, a possible pattern here would be a sterile neutrino. You see very different structure. So here, you're trying to use the simulations to understand what the structure of the small lumps would be. So to summarize this part, I think the dark matter halos are the fundamental nonlinear units we think in our universe. You know, all lumps are made mostly of dark matter. 80% dark matter, 20% ordinary matter. They have a particular structure, and they have many small pieces in between them. And they're the places where we think the galaxy is formed by the gas cooling off. But everything we know about them, these are all very nonlinear objects. I would argue their abundance, their structure, their evolution, and their clustering, what we know, or we think we know, has been entirely the result of numerical simulation. So this is the point where, in the theory, the numerical simulation allows us to take what comes from to us, what we think we know about the early universe that we see in the microwave background, and predict what the universe today should look like. So if we ask what's going to happen in the near future, I think the small-scale structure will tell us perhaps about the nature of the dark matter, whether it's warm or cold, whether it's really non-interaction, it has some additional interactions. Perhaps we can find the interaction with the dark energy. The very, very small scale structure is important for the annihilation signal, and perhaps also for the direct detection signal, which Bernard Saddeley will talk about later. And then details on large scales are very important for understanding precision cosmology. Once we need to predict things at the levels of accuracy of a few percent as opposed to factors of 2, then there are many, many effects that you have to take care of. How are things going to prove? This is the biggest calculation done in this field in terms of the number of individual elements simulated, from 100 to 10 billion. And this is the year of the calculation. And this was the one I showed you the fly-through. Already 5 years later, we're up here. The ability of computers has been increasing. So I think we will continue to get better simulations. And the progress here is actually roughly equally due to the hardware, the computers themselves, and to the algorithms, which have also been improving. So I think we can say that the computer power is actually the fastest growing aspect of astrophysics, in the sense that the capabilities are doubling every 18 months. Whether we learn something new, of course, I think is debatable, but anyway. So they've become the primary tool for confronting objects with theoretical ideas about the early universe, because they allow us to bridge between the linear early universe and the nonlinear universe today. I think, this all looks good, but you shouldn't believe pretty pictures, because in the end, what you get out is only as good as what you put in. If you put in garbage, you get garbage out. And for many problems, so we're not actually limited by the computing power any longer, but by our ability to put in the correct physics, and I suspect this will continue to be the case.